Today we're going to talk about electromagnetic radiation. And electromagnetic radiation is simply the type of energy that travels through space in the form of waves. And we can represent this electromagnetic radiation by using or showing something called the electromagnetic spectrum, and it just shows these different types of waves in order. On this particular spectrum, we are looking at the waves in order from what I call the triple L side. The triple L side is the side that has the long wavelength, the low frequency, and the low energy. And on the opposite side of the electromagnetic spectrum, we have the short wavelength, the high frequency, and the high energy. I would expect you on the test to be able to just maybe on scratch paper draw a line and be able to show the different types of electromagnetic radiation in order. We have radio, microwave, infrared. I would expect you to know that visible comes next. That's the only part that we can actually see. Ultraviolet, X-ray, and gamma ray. And I would expect you to know that visible light can be split into and spread out into the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. We use the mnemonic device Roy G. Biv to help us remember the order of that spectrum. A lot of books are leaving out indigo, but I like indigo, so I'm going to leave it in. So Roy G. Biv helps us remember that order: red, orange, yellow, green, blue, indigo, violet. And if I were to ask you, for instance, which color has the lower frequency, orange light or blue light, we would find orange and blue on the spectrum. And since orange is closer to the left-hand low frequency side, that would have the lowest frequency. Perhaps maybe I would ask you which has the shorter wavelength, infrared or X-ray. Since X-rays are closer to the short wavelength side of the spectrum, then I would be able to answer X-rays have the shortest wavelength. So using that spectrum and knowing the triple L side versus the high side, we can make those or answer those kinds of questions. I would also expect you to be able to tell me different characteristics of a typical wave. I would expect you to be able to show me that wavelength, which by the way has a symbol, the Greek letter lambda. It kind of looks like an upside down Y when you write it handwritten. And that wavelength goes from a crest to a crest or a trough to a trough on a particular wave. And I would expect you to know that amplitude is the height of the wave from its rest position. We think of the rest position as being this imaginary line that crosses through the wave. Amplitude is either the distance from the rest position to a crest or the rest position to a trough, the low point. I would expect you to know what frequency is. Frequency, if you look at the symbol for frequency, it looks like a V. It's actually a Greek letter nu, N-U. It looks like a blocked off V with kind of edges on the sides if you handwrite it. The frequency is how many waves pass a point each second. And if we look on this particular wave, we have a wave that starts here, and the next equivalent point on the wave as we go up and down to the rest position and back up to the rest position, there's one complete wave cycle. There's one wave. There's two waves. And finally, three waves. We would say if those waves passed a point in 1 second, that particular set of waves had a frequency of 3, what we call reciprocal seconds. That's a very kind of a strange unit. We haven't seen one like that before, used one like that before. You can also write it as 3 seconds to the -1 with just an S, and sometimes you will see it as 3, they'll call them per seconds with 1 over seconds, or 1 over S or 1 over SEC. So those are some different ways that that's represented, and we'll see examples of why it has to have those units here in just a moment when we start looking at the problems. We also know that the speed of an electromagnetic wave is the same for all types of electromagnetic waves. If they're in a vacuum, it's a constant c, and that constant is 3.00 times 10 to the 8th meters per second. So radio waves, light waves, gamma rays, all of those have the same speed of light in the same medium. And again, in a vacuum would be 3 times 10 to the 8th meters per second. We have 3 equations that will help us relate 3 different characteristics or 3 different properties of a wave. We have energy, we have frequency, and we have wavelength. This particular equation relates wavelength and frequency to each other, and they were related to each other according to the speed of light. And it says that the speed of light is equal to the wavelength times the frequency. Notice that wavelength has to be in meters and frequency has to be in reciprocal seconds. Another term for reciprocal seconds is hertz, and you will often hear about radio stations being broadcasted in certain numbers of hertz. So if we look at this first problem, again, this is the one that's going to relate frequency and wavelength. So we see this first example here, and it says that the brilliant red colors seen in fireworks are due to the emission of light with wavelengths around 650 nanometers. There's one piece of information. When strontium salts, such as strontium nitrate and strontium carbonate, are heated, calculate the frequency of red light. So we want to know the frequency. If we do have that wavelength, and it represents it the same way but in scientific notation of 6.50 times 10 to the second nanometers. So once we know we're dealing with frequency, and that is giving us information about wavelength, that's how we know we're dealing with this particular equation. So writing that equation, C equals lambda nu. The first thing I want to do is to solve this equation for the variable I'm looking for, which is frequency. So I'm going to solve it for this blocked off letter V. Remember, if we want to solve for this, we need to divide both sides by lambda, which is going to reduce lambda to 1, or cancel lambda is how we usually refer to it in chemistry, as you remember. And we end up with the fact that frequency is equal to C over lambda. Now also recall that I like to have the variable I'm looking for on the left, so I'm going to write it like this. Frequency equals C over lambda. So let's solve for that. I know that C is a constant. C is, as you remember, 3.00 times 10 to the 8th meters per second. I'm going to be dividing that by the wavelength. Now the wavelength here is in nanometers. Remember, it has to be put into the problem in meters, so we've got to convert it. Units are incredibly important. If we don't put it in meters, it's never going to cancel right here with our meter value. So let's look at this. We've got 6.50 times 10 to the second nanometers, and we want to convert that to meters. Now remember how we do this. We know that nanometers, nano is 10 to the minus 9th. We know that meters, since it has no prefix, the base unit, 10 to the 0. Going from -9 to 0, our unit is getting bigger by 9 places. So our number has to get smaller by 9 places. So we end up with a value of 6.50 times 10 to the 2 minus 9. 2 smaller by 9 is -7. So that's our value for our wavelength. So So once again, our wavelength is 6.50 times 10 to the negative 7th meters. That's going to cancel meters, leave us with seconds on the bottom. When meters cancel or reduce to 1, we end up with 1 over seconds, or reciprocal seconds. So our answer here is going to be 4.62 times 10 to the 14th reciprocal seconds. I'm going to write it this way. Now also remember that a reciprocal second is also a hertz, so it's also 4.62 times 10 to the 14th hertz. Okay, so let's look at another problem. Let's say this time we want to show the relationship between energy and frequency. So this particular equation is going to show us the relationship between energy and frequency. This relationship was discovered by Max Planck, and the constant that we use in this equation is called Planck's constant, and it's 6.626 times 10 to the negative 34th joule seconds. So that's a value that you want to I'm going to give it to you on tests as I am the speed of light, but you have to know what it refers to and where to find it. So, looking at this particular problem, what is the frequency of light that has an energy of 2.85 times 10 to the negative 22nd joule? So it's looking for frequency, and it's asking, and it's giving us information about energy. We know then that it's asking us to use this equation. Change in energy is equal to Planck's constant times frequency. We're solving for frequency, so once again, remember, to solve for frequency, we're going to need to divide both sides by h, Planck's constant. We end up with frequency being equal to energy over Planck's constant. Remember, I like to write that with the variable that I'm solving for on the left. It's kind of a thing for me. So frequency then is going to be equal to the energy, which is 2.85 times 10 to the negative 22nd joules, divided by Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. Now notice once again, when we cancel, joules cancel, we're left with 1 over seconds, or reciprocal seconds again, which is our frequency unit. When we divide that, we get this is frequency again, is going to be 4.30 times 10 to the 11th reciprocal seconds. And what's the other name for reciprocal second? Yes, hertz. So 4.30 times 10 to the 11th hertz would be another way of representing it that you'll see once in a while. I prefer reciprocal seconds. That's really what I want you to use. Our final representation, our final equation then, is going to show the relationship between energy and wavelength. So this is our energy and wavelength equation, and when you read a problem, you're simply going to decide what pieces of information does it ask for and give you, and that's going to tell you which equation of these three that you're going to use. So energy is equal to, or energy is being related to wavelength in this particular equation. So we look at the example problem. It says the blue color in fireworks is often achieved by heating cuprous chloride to about 1200 degrees. Then the compound emits blue light having a wavelength of 450 nanometers. What is the increment of energy? What is the energy, or quantum, small amount of energy, that is emitted at that wavelength? So we've got this wavelength as a piece of information. And since we already know, hopefully remember from the last example, from a previous example, that we need to have wavelength in meters, not nanometers, let's go ahead and convert that. And it is so much easier if you'll go ahead and take this 450 and change it to scientific notation. 4.5 times 10 to the second nanometers. It's going to be equal to how many meters? We've got the same conversion. Remember, nano is 10 to the negative 9th, and meter 10 to the 0 since it has no prefix. That means the unit's going from negative 9 to 0. It's getting bigger by 9 places. So our number up here, symmetric seesaw, has to get smaller by 9 places. So our answer becomes 4.5 times 10 to the negative 7th for our meter value. So let's solve this problem. Energy and wavelength, we know that E is equal to hc over lambda. We are actually solving for energy this time, so we don't need to rearrange the equation. E then is equal to Planck's constant, 6.626 times 10 to the negative 34th joule seconds, times the speed of light, also a constant. Look back earlier to find out what that is, 3.00 times 10 to the 8th meters per second. And we're going to divide that by the wavelength we just figured out up here of 4.5 times 10 to the negative 7th meters. Notice what cancels. We're going to cancel meters. We're going to cancel seconds, and we're left with joules. Is that a valid unit for energy? Yes, it is. So energy then is going to be equal to 6.626 times 10 to the negative 34th times 3.00 times 10 to the 8th divided by 4.5 times 10 to the negative 7th. And we come up with a value for that in our calculators of 4.42 times 10 to the negative 19th joules.